Hello there, Mr. Sutton here, bringing you the AB Calculus 5-7 homework solutions on properties of definite integrals.
For number 1, we're given the fact that g is a continuous function and the integral from negative 3 to 0 of g of t dt is the square root of 2. Based off of this, we're going to find a few different things. So for part A, we're trying to find the integral from 0 to negative 3 of g of t dt. So when you're integrating backwards, you're essentially taking a negative version of the original integral. So this is really just equivalent to negative whatever this stuff was. Now this stuff in the beginning came out to the square root of 2, so this is then the negative square root of 2. For part B, we're trying to find the integral from negative 3 to 0 of g of u du. So changing the variable of integration we've seen does not actually change the value of anything. This is still going to come out to the square root of 2. For part C, we're trying to find the integral from negative 3 to 0 of negative g of x dx. So there's two things going on here. First, we have this change of variable from t to x, which doesn't really change anything at all. We also have this negative multiplier in here. We can actually pull that outside as a constant. This is just essentially negative 1. So we'll put that outside. And now we're just going to have negative integral from negative 3 to 0 of g of x. The original integral here was radical 2, so this comes out to negative radical 2. For part D of this problem, we're doing integral from negative 3 to 0 of g of r dr over radical 2. So again, this change of variable is not going to affect anything at all. What will affect things is dividing by this radical 2. We can actually pull that out as a constant multiplier. It's like having 1 over radical 2 outside here. So we have 1 over radical 2 times just the regular integral that we've been dealing with this whole time now. So 1 over radical 2 times radical 2, those are going to cancel. This just comes out to 1.
For this problem, we have f and g as continuous functions, and we know the integral from 2 to 6 of f is 5, and from 6 to 2 of g is 7. Based off of that, we want the integral from 2 to 6 of 3f of x plus g of x dx. So we're going to tackle this problem with a divide and conquer approach. We can split this integral up since we're adding the stuff inside the integrand. So 3f of x can get its own integral, and we're going to add that to the integral of g of x, all of those from 2 to 6. Now when I split this up, I also am going to take this 3 outside the f integral. So it's going to look like this. We're going to have 3 times the integral from 2 to 6 of just f of x dx, plus 2 to 6 integral of g of x dx. All right, so let's see what we know here. We know that the integral from 2 to 6 of f is 5. They told us that up here. So this first piece is really just 3 times 5. Next, we know that the integral from 6 to 2 of the g function is 7. If we reverse the limits of integration, we're basically changing the sign of this because we're integrating backwards. So this is really going to come out to negative 7. So this is going to be then 15 minus 7, which gives us 8, and that is answer choice B. On this question, we have f as a function such that f of negative x equals negative f of x. So that's going to be important a little bit later on, but moving on here, if the integral from 0 to 2 of f is 5, we want the integral from negative 2 to 2 of f of x plus 6. So I'm going to split this up a little bit so I can do a little divide and conquer with these. So I'm going to take the integral from negative 2 to 2 of f of x plus the integral from negative 2 to 2 of 6. So this 6 integral here, I can deal with this pretty easily. This is just going to be a horizontal line, y equals 6, and we're just asking for the area underneath that. So before we do that, though, we need to take care of this negative 2 to 2 f of x piece over here. So we know the integral from 0 to 2 of f of x equals 5. We don't know anything about negative 2 to 0, but just to give ourselves a chance of getting through this one, I'm going to split this one up into the integral from negative 2 to 0 plus the integral from 0 to 2 of f of x. And we'll just leave the 6 dx over here. So now, again, I don't know what to do just yet with this first integral, but I at least know that the integral from 0 to 2 is 5. So now I just have to reason through what this first integral has to be. Now, to do this, we look back at the original problem here. They told us that f of negative x equals negative f of x. What that means is that this is an odd function. And if something is an odd function, for example, like the cube root function or y equals x or sine, that means that it is symmetrical about the origin, which means that all the area in the first quadrant is going to cancel out negative area in the third quadrant. That's kitty corner to it. So what this means basically is if there is 5 units of area from 0 to 2, then there must be negative 5 units of area from negative 2 to 0. So this first integral here, this has to be negative 5. So that's going to be negative 5 then, plus positive 5. And then now we have to deal with this last piece here. This is the area under the horizontal line y equals 6. That is a base of, let's see, negative 2 to 2 is 4, height of 6, so that's 24 altogether. And then that just adds up to 24. Choice C.
For number 4, we're trying to find the integral from negative 1 to 9 of 3 times f of x, where f of x is defined up here in the graph, plus 2. So to help us out here, we're going to use the properties of integrals where we can split this up. So I'm going to give 3f of x its own integral from negative 1 to 9, and I'll do the same for 2. And while I'm at it, I'm going to move this 3 outside the integral because I'm allowed to do that. All right, so let's keep going with this divide and conquer approach. Now for this integral of the f function, I'm essentially finding the area between this piecewise function and the x-axis for this piece of it. And I've got a 3 multiplied by whatever I get for that area. So I have 3 times, and now my first area is this trapezoid area. I have a base of 3 and a base of 4. I'll take half of that and multiply it by the height of 1, and this is going to be negative area because it's under the x-axis. So we have 3 times negative 4 plus 3 over 2 times 1. This is negative 3.5, by the way. We'll get back to that. Now our next area, we have this triangle from 3 to 9. This is going to be 1/2 times a base of 6 times a height of 2. So this half and this 2 cancel. That's just 6. And then over here, we've got basically a horizontal line from here to here. This gives us a rectangle that we're finding the area of. This rectangle has a base of 10 going from negative 1 to 9 and a height of 2. So just 2 times 10 out there. All right, let's crunch these numbers. If this were free response, we could just leave it. But because the answer choices are fully simplified, we have to keep going. So we've got negative 3.5 plus 6 inside there and a 20 outside. Negative 3.5 plus 6, that's 2.5, times 3 is 7.5, plus 20 is 27.5, which gives us answer choice C. For number 5, I want to find the integral from negative 10 to 6 of g of x, given these other 2 integrals here. So one way we could do this is we could split this up using these 2 different integrals. I need to write 2 integrals, one of which starts with a negative 10 and the other of which ends with a 6. The only of these integrals with a negative 10 in it is this first integral here, so I would have to basically turn this upside down, and then if I add the integral of g from negative 10 to 4 to the integral from 4 to 6 of g, that would give me the integral from negative 10 to positive 6. So that's what I'm going to do. So I've turned this first integral upside down. That means, since I switched my limits of integration, since I'm going backwards, this negative 3 will now be a positive 3 here. And we didn't make any changes to this other integral, so this is still plus 5. 3 plus 5 gives us 8. Choice D. For number 6, we're given 2 continuous functions, f and g, and we're told that f is always positive. Based on that, which of the following has to be true? So this is one of those where you have to eliminate what you can and then pick one of these answer choices. So let's take a look at these one at a time. Now, some of these are actually properties of integrals, so we should be able to tell whether they're true or not right off the bat. Like I know choice 2 here, this is one where you're splitting up your integral into 2 mini integrals that have the same limits of integration over addition. We've seen we are allowed to do this, so 2 at least is true. But eliminating some of these other ones might be a little trickier. So as a little trick on this one, I'm going to actually plug in some real numbers and see what comes out and what I can disprove. I'm going to let the f and g functions both take on a value of 1. We'll just make them both constant functions of 1. And then for my lower limit, I'll have 0. For my upper limit, I'll have 2. Let's see what still makes sense after we plug all this in here. So for option 1, we've got integral from 0 to 2 then of 1 times 1. Well, the integral from 0 to 2 of 1, that's just, let's see, a rectangle with a height of 1 and a base of 2. So that's 2. Over here, I've got integral from 0 to 2 of 1 times another integral from 0 to 2 of 1. Each of these integrals individually has a value of 2. So this is 2 times 2 over on the right side, which is 4, which does not equal the 2 that we had on the left side. So because 2 does not equal 4, using these numbers at least, we can eliminate choice 1. Let's keep going. Choice 2, we already confirmed this is one of our properties, but just for the sake of argument, we've got 1 plus 1, so integral of 2 from 0 to 2. That's going to be 4. And over here, we have integral from 0 to 2 of 1 plus essentially the same thing. So that's 2 plus 2, which is also 4. So that's by itself not enough to prove that this is true. We might have just gotten lucky with the numbers that we picked, but at least we can't eliminate it. So if we can eliminate choice 3, none of the above is not an option, so then it would have to be choice 2. So let's take a look now at option 3. So on the left side, we have integral from 0 to 2 of, well, the square root of 1 is 1. So that's just a value of 2 on the left side. On the right side, we're taking the integral from 0 to 2 of 1 right away, which is 2, and then we're square rooting that after the fact. So that comes out to radical 2 on the right side. Since 2 and radical 2 are not the same number, we can eliminate very quickly choice 3. So again, 2 is actually a property of integrals, and none isn't one of our options. So we're going to have to go with 2 only, choice B. Number 7 is a fun one for properties of integrals. So for this one, f and g are continuous functions, and we're given that a is less than c, which is less than b. So they're essentially saying c is some number between a and b. And we're giving these 4 different integrals. Integral of a to b of f is p, c to b of that function is q, and then a to b of g is r, and c to b of g gives us s. Based off of that, we want the integral from a to c of f minus g. So to make my life easier, I'm going to start by splitting this up into 2 functions, or 2 integrals rather. So I've got integral from a to c of f minus integral from a to c of g. All right, so now that I've split up the 2 integrals using subtraction, I'm going to split each of these integrals up now into more bite-sized pieces. If you look at what they gave us for information in the beginning, they didn't give us anything involving both a and c at the same time. So we're going to have to use our additivity rule to unadd this into 2 different integrals. The first integral's got to start with an a, the second integral's got to end with a c. We have an integral for f that starts with an a. It's this a to b one here. So let's start with that. Plus, we want integral from b to c. And we're going to have to pay for that later on, but that's what we want. Now over here, for our g function, we want to split this one up as well. I want the integral from a to b of g plus the integral from b to c. I'm going to put all of that in a big parentheses just so I don't mess up my signs, because I'm subtracting all of this stuff for this integral at once. Okay, so here's the part where we actually insert these different letters for these integrals. So integral of f from a to b. Well, that's this p constant here. So I have a p, and then I don't have an integral from b to c for f. I do have a c to b, though. That was q. So if I want b to c going backwards, that's going to be negative q. So we have p minus q. What's inside our parentheses here? G from a to b came out to r, and then g from b to c, that's backwards from c to b here, so that'll be a negative s. All right, time to distribute. So I've got p minus q minus r plus s. And really, that was just half the battle. We have to actually pick the right answer choice. These all look very similar. So we're starting with a P, and we're subtracting Q, so that narrows it down to choices A, B, and C. Next, we're subtracting R, so now it's down to B and C. And finally, we're adding S, so that allows us to pick choice B. For number 8, we want to find the integral from 0 to 5 of 3 plus 2 times f of x. And all they gave us was some information on f of x from 0 to 3 and also from 3 to 5. I'm going to start by splitting this up. So I'm going to do integral from 0 to 5 of 3 plus integral from 0 to 5 of 2 f of x. And while I'm at it, I'll pull that 2 outside the integral, like so. All right, so let's tackle each of these individually. So this integral from 0 to 5 of 3 dx, this one's going to be pretty easy to compute. This is just a rectangle with a height of 3 and a base of 5, so we'll deal with that in a sec. This next one, though, we don't have any information on the integral from 0 all the way to 5, but we can split this up into 0 to 3 integral of f and the 3 to 5 integral of f, adding those together using our additivity rule. So we've done that split in this parentheses here for you. Next, we've got our rectangle over here, height of 3, base of 5, so that's 3 times 5, or 15. And in here, we had 6 for this first integral, and they also gave us the second integral was 4. So we've got 15 plus 2 times 10 comes out to 35. Choice D. For number 9, I'm trying to find the value of the integral from 0 to 3 of half of f of x minus 3 times g of x, given all these different integral values of f and g. So in order to do this, at some point, I'm going to need to know the value of 0 to 3 integral of f, and the same thing for g. Let's do the f one first. So to find the 0 to 3 integral of f, well, I know 0 to 6 for f, and I know 3 to 6. If I take 0 to 6 area and subtract the 3 to 6 area, like so, then what I get left over ought to just be my area between 0 and 3. And you can do this with additivity too. I'm just going for the intuitive approach on this. So we've got essentially 9 minus 5, which gives us an area of 4. Okay, we can work with this. Now let's tackle the next one. We want the area from 0 to 3 of g of x. And we're pretty close, right? This is exactly what we need, but it's upside down. So if I want to integrate backwards from what this is doing and go from 0 to 3, I just have to negate the area here and make this a positive 7. All right, so at this point now we're going to go through and split this integral up. And this is a two-step process that I kind of do all at once. We can split them up into two different integrals that are being subtracted because of the subtraction in here. And the first integral we can take out a 1/2. Second integral we can take out a 3. Like so. So I have 1/2 times integral from 0 to 3 of f minus 3 times integral of 0 to 3 of g. Well, f we just found, that was 4, so this is half of 4, minus we've got 3 times 7. So half of 4 is 2, 3 times 7 is 21, 2 minus 21 gives us negative 19. Choice B.